Well, good morning or good afternoon, depending on when this is played. My name is Dave Martin, and I'm from the University of Delaware. And it's my pleasure to be involved in this special symposium for the ACS Fall 2020 meeting in honor of Qinghuang Lin receiving the Tess Award from the PMSE division. So it's been an unusual time, and sorry I can't be there in person, but just wanted to congratulate Qinghuang on this well-deserved award. He and I have known each other since our days at the University of Michigan when Qinghuang was a graduate student in Professor Albert Yi's lab, and I was a relatively young assistant professor at the time. And we had a lot of very nice conversations about liquid crystalline epoxies, I recall fondly. And since that time, we've kept in touch. And over the last few years, we've had a lot of interactions related to PMSE business. And it's always been a pleasure to interact with Qinghuang and to learn about the work that he's been doing at IBM, to look at DNA through small holes. My own group has been interested in looking at conjugated polymers for a number of device applications. So that's what I want to tell you about today. We've been looking in some detail at a conjugated polythiophene called PDOT, which has really become quite popular over recent years. And what I want to tell you about today is the newest work we've been doing to look at a very interesting copolymer of PDOT that has a maleimide functionality on it. And those of you who are familiar with maleimide chemistry will appreciate that having an maleimide group on a thiophene opens up a whole wide world of new synthetic opportunities for tailoring the properties of these materials. All right, so let me start by saying that everything you're going to hear about today was done by somebody else. And it's really because of these talented graduate students that those of us faculty members get anything done. This is particularly true for me over the last year and a half, because in February of last year, I assumed the position of the Associate Dean for Research and Entrepreneurship in the College of Engineering at Delaware. And so it's just been that much more difficult for me to really spend time hanging out in the laboratory. But these guys are really fantastic. Let me call out in particular Samadan Nagane. Dr. Nagane came to Delaware in April of last year and really made very rapid progress, working at the time on a DARPA project that we had. And since then, I've been supporting him with discretionary funding that has enabled us to create these new monomers that I'm going to be talking about today. So he, at the moment, is back in India. He went back to get his wife and family and bring them back to Delaware. But just around that time, the coronavirus hit. And so we've been doing what we can to work with him and are currently setting up a lab that he can do some work in locally in India and then send us samples to characterize in more detail. All right, so about 5 years ago, I had just finished serving as the Material Science Engineering Department Chair. And in order to rehabilitate my brain, I took the time to write a review article. This was unusual in the sense that I'm the sole author on this paper. So my students, I really appreciated, again, how much work is involved in getting all the references together and the figure approvals have appeared elsewhere altogether. And anyway, the work that we've been doing in my lab has really been centered around materials that can interface inorganic, electronic, biomedical devices of various sorts with living tissues of various sorts. So there are a whole number of applications of these devices: pacemakers, of course, deep brain stimulator, glucose sensors, cochlear implants, and even most recently an FDA-approved retinal implant that is hoping to restore some sense of vision. There are also implants that are going into the brain for brain-machine interfaces, including the group at Michigan that we were interacting with a lot that makes electrodes that go into the outer regions of the cortex. And that technology from the Center for Neurocommunication Technology was spun off into a small company called Neural Nexus that my colleague Daryl Kipke is quite involved in. There's also work that's come out of the University of Utah to make a microelectrode array that's more of a pincushion type design. But in all these devices, it's really some kind of an electrode made out of stainless steel, gold, iridium, platinum, or a silicon substrate that's trying to talk to tissue. So what we have is an interface where you've got an inorganic, hard, rigid, flat, crystalline device that's trying to talk to soft, squishy, organic, and wet, ionically conductive tissue. And so conjugated polymers are very interesting because of the fact that they have physical properties that are intermediate to the two extremes we're trying to talk to here. But in particular, they're very interesting because of the fact that the devices talk in solid state by electrons and holes. The tissue itself talks ionically. And so conjugated polymers are nice because they have the ability to conduct charge both electronically and ionically. So very interesting because of that. Now, as I mentioned, the polymer that has received a lot of attention is this chemically stable polythiophene called PDOT. PDOT is available commercially from Heraeus. They bought the technology originally developed from Bayer. And commercially, it's sold as a suspension, so you get it in a bottle and you can cast it as a film. My colleagues in France add a cross-linking agent called GOPS that creates a stable film that then won't redissolve when it's implanted into the body. We like to use electrochemistry because electrochemistry allows us to do the oxidation polymerization reaction right on the electrode surface so we can direct where it goes. We can tailor the counterion quite easily, and we can then create also very precisely tailored films that have different morphologies by using, say, dissolvable substrates or different constructs that we grow the polymer around. And in fact, we've even done this polymerization in living tissue. So we've grown the polymer in the brain, we've grown it in the hippocampus, we've grown it in peripheral nerve, and that's one of the other interesting angles that can be explored here. Now, in terms of a materials design problem, the stability of this molecule comes from the fact that there's no hydrogens pendant on the conjugated backbone. And again, you get this transport where you have electrons and holes moving along the molecular backbone, and then some counterions that are putting a little bit of charge on the polymer backbone. So you get both electron transport and ion transport. If you look at the deposition of conjugated polymers onto a device as a function of time, this is a particular device, a Michigan-style neuroelectrode, about 150 micron wide silicon substrate with metal electrodes 40 microns in diameter. You send different amounts of charge through it, and you will deposit more and more conjugated polymer as more current runs through the electrode. If you look at the impedance of these electrodes, and we like to look at the impedance as a function of frequency, do what's called impedance spectroscopy. For biomedical devices, the important frequencies are those that are at 1,000 hertz and below. A neural event is typically 1 millisecond in length. And so if you look at the impedance at 1,000 hertz as a function of time, you see that it drops dramatically, sometimes 2 orders of magnitude, sometimes 3, depending upon the precise conditions. And the reason for this, you can appreciate just from looking at the SEM images in the upper right. So the conjugated polymer is not a better conductor than the underlying metal, but it has a whole lot of surface area. And so we're creating a thin film that's essentially acting, as my colleague George Maliaris likes to call it, as a volumetric capacitor. So there's just lots of room for charge exchange, particularly when you're going to put a device into an ionic solution like a tissue. And so you're pulling cations in and out, you're exchanging that with hole transport in the polymer. You exchange holes with electrons at the polymer metal interface, and typically these devices are operated at 0 net voltage so that you're not doing any electrochemistry. So that very dramatic drop in impedance is extremely important for biomedical devices of various sorts. It opens up the opportunity for building lots of interesting specialized devices that would do particular things. This is just one example from our own group, looking at the use of these materials as chemical sensors, in this case for a growth factor protein called VEGF. That's very important for certain eye diseases. So this was done in collaboration with Ray Ayezi at the Mayo Clinic, and we were able to get very sensitive detection of VEGF by using this system where we would measure changes in electrical current in the presence of the VEGF. So as you can imagine, there's a lot of commercial interest. I just would mention, we actually spun a small company off just before I left the University of Michigan and formed a company, Biotectics. The principals there were Sarah Burns, a former postdoc, who unfortunately passed away just a couple years ago, and Jeff Hendricks, who was the director of engineering. The technology for Biotectics lived on for 10 years and then was fully acquired by Heraeus Medical Components, an arm of the Heraeus company that sells the PDOT, and is now subsumed and is behind the firewall. So I now no longer have any insight into what's actually going on in a business sense, and no longer a conflict of interest. And I would just point out that there are a number of other people, including this gentleman, Elon Musk, who has looked at the use of PDOT. Elon's company, Neuralink, is making a brain-machine interface technology, and one of the critical components to lower the impedance of those electrodes is to electrochemically deposit, following procedures we developed, PDOT coatings onto those electrodes before they're inserted into animals. Okay, so PDOT is great, but that's 10, 15 years ago technology. What's happened in the meantime? Well, PDOT itself has a lot of advantages, but a number of disadvantages. One thing is PDOT has not yet been approved for use on a particular device, although it's very close in a number of applications. Let me point out, by the way, that the FDA does not approve materials per se, they approve devices. And so the issue, if you have a new material, is to get your material approved for use on a particular device. There are also a number of other applications, or I should say limitations. There aren't any specific interactions with tissue for normal PDOT. There are some issues with brittleness and adhesion to substrates. The normal EDOT monomer is relatively cytotoxic, and there's no way of changing the mechanical properties all that much. The only reaction that occurs is the polymerization or reaction across the thiophene. And so our new monomers have addressed all of these different issues. So one of the first new monomers that we developed back still at Michigan was the carboxylic acid functionality. So my colleague Jinseng Kim helped to create this EDOT acid monomer that we have been examining in some detail since. Right after I got to Delaware, I was at the University of Santa Barbara and met Katie Feldman, who at the time was working with Craig Hawker. She brought in thiol-ene click chemistry. And so we've created a whole series of different thiol-ene functionalized, click functionalized EDOTs and ProDOTs, ProDOT having an extra carbon between the two oxygens, so it's propylene dioxythiophene. You can have either one ene dangling off, or you can have two enes dangling off. So this was some work by a subsequent graduate student, Ben Wei, where he had the difunctionalized ProDOT, and he used different thiols, one being hydrophobic, which shut down the charge, one hydrophilic, which created a nice wet surface and essentially didn't change the charge transport much at all, and then one that had an electroactive ferrocene and really caused a lot of electrical activity that we could easily see when we did CP. So the most recent monomers are, again, different in the sense that we've made a PDOT aldehyde, dopamide, and tyramine, but the real important one of all of these is this PDOT maleimide. And so PDOT maleimide is very interesting because if you've got maleimide, you've got access to a wide variety of different chemical reactions, either with furans, thiols, amines, azides, or polymerizing the maleimide or the thiophene itself. So you have a whole huge laundry list of chemical reactions that you can use to optimize. And the maleimide itself can undergo a reaction similar to the thioene, where you have now a thiol on a bioactive molecule, and you can click on your bioactive molecule to make a functionalized monomer, or you can make the polymer and click it onto the polymer at the end. And again, some of the groups we've looked at so far include adamantane, relatively bulky hydrophobic group, a surface active molecule like cholesterol, and an amino acid. So again, just to emphasize that this degree of processability and synthetic flexibility allows us to consider either making monomers into polymers and then functionalizing the polymer, or making a monomer and then polymerizing the monomer to make the polymer. The preferred route depends on really what application you're after and what the other limitations are. The biofunctionalized thiophenes tend to be less cytotoxic, but they also tend to be more difficult to polymerize because they become more hydrophilic. And so getting the polymer to crash out of solution using the electrochemistry that we prefer is more difficult when the monomer becomes more hydrophilic. So just some results showing that we've obtained the molecules that we're after. Here is the synthesis route and the proton NMR that confirms that we've made the E-dot maleimide. Here is the synthesis route for putting dopamine on. The dopamine itself, an interesting molecule, can be used as the precursor for synthetic melanins and is found in the body naturally. And again, the proton NMR confirming that we got it. And here's the E-dot cholesterol showing that we've made thiophenes with this surface active and potentially liquid crystalline cholesterol unit on the side. Just another slide showing that the azide group itself can be used and gives you the ability to control cross-linking. And then these are optical micrographs showing that we have indeed deposited the polymer on the central electrode here and have measured the impedance spectroscopy and are comparing these results to those of other studies that we've done in the past and other materials. So you can either lower the impedance or increase the impedance depending upon what particular application you're after. Right now, we're creating a bunch of sensors, making organic electrochemical transistors where these new functionalized E-dots serve as the channel layer of a field effect transistor that's in contact with the ionic solution, following work that has gone on elsewhere, including George Maliaris, Jonathan Ribnay, and others. I'll just conclude by saying we've also continuing to do a bunch of TEM. So my lab is currently actively exploring the use of liquid cell TEM, especially using an electrochemical cell. We can do the polymerization in the transmission electron microscope. And here's an example of P-dot, and in this case, polydopamine, growing on an electrode. This happens to be a hummingbird holder that we are putting into our 200 kV telos. All right, so this is my conclusion slide. We've got new monomers, we're characterizing them, we're doing a lot of bioelectronic applications. And let me just pause and thank the organizers and congratulate Qinghuang for the award. Thanks for your attention.